Welcome back, students. Today, we are going to attempt to take the particle in the box model that we talked about last time and attempt to make it more real. So we're going to do that in two ways. The first way we're going to do that is by discussing the particle in a three-dimensional box rather than a one-dimensional box. And the next thing we're going to do is discuss a particle that's stuck in a box, not by an infinitely deep potential, but by a finite potential. So as we go through these problems, what you'll see is that the three-dimensional box is actually pretty straightforward based on the one-dimensional box, but the finite depth box is not as straightforward. So we're going to go through carefully and kind of show how the model has to adapt for these two situations. So to put the particle in a three-dimensional box, we have to adapt it in a couple of ways. Now, the first way we have to adapt it is, of course, by making three dimensions. So to make three dimensions in our Schrodinger equation, we can simply just change the equation from a function based on x to a function based on x, y, and z, so three dimensions. And to do that, we get the following. So we have a potential as shown here. That's equal to 0 only when our particle is within some box that's based on the coordinates x, y, and z. And otherwise, it is equal to infinity. So this is a direct extension of our one-dimensional box. Now, how do we solve this equation that looks much more complex? It turns out that it's actually rather straightforward. And we have to introduce one reasonable assumption. And that is, since our potential energy function of x, y, and z is independent of x, y, and z, so there's no x or y or z dependence, it's just either 0 or infinity. What we can do is achieve a separation of variables and assume that our function is three independent functions, only based on x, y, or z. So our wave function of x, y, and z is therefore equal to the product of three functions. So we're going to write x of x, y of y, and z of z. And we can do that because our wave function is independent of these variables. It doesn't change. So that as we change in the x direction, the wave function doesn't change in the y direction or anything like that. So how does this help us actually solve the problem? Well, we can plug this in to the equation up here, and we're going to get the following. So to kind of simplify the math here, I'm going to do two steps at once. So what happens as we plug in x of x, y of y, and z of here is we'll get an energy function times each of these independent functions. And then I'm going to divide the whole equation by this product of these three functions. And why do I want to do that? Let's check it out. So first, let's evaluate what happens if I take two derivatives with respect to x of my function x of x, y of y, and z of z. Well, the y and z functions don't have any x components, so they're simply constants, so we don't take the derivatives of them. And then I just have to take two derivatives of whatever my x function is. So this function is simply y of y times z of z times two derivatives of x with respect to x. And this is going to be true for every single term here, every partial derivative term in my Schrodinger equation. And so if I divide this by the wave function x of x, y of y, and z of z, so I'll just go ahead and divide this here. So if I divide like this, well, we'll notice that the y and z components are going to cancel out. And what I'm left with is 1 over x as a function of x times two derivatives of x with respect to x. And I can do that for all three terms, which will simplify my wave equation into the following. I'll have negative h bar squared over 2m times 1 over x of x times two derivatives of x with respect to x. And then I'll have the same for y and z. And what we'll note is that what are these going to be equal to? Well, all that's left on my right-hand side of the equation is simply the constant, that's the energy that we're going to get out of here. So what can we do with that? Well, what we have is a function. So on this side, we have three independent terms that are derivatives of these three different variables. And when we sum these together, they need to equal a constant. So what that means is that we can't have any x terms left over in this equation. If we did, when we added it to the y and z terms, we wouldn't just have a constant e on the other side of the equation. So that means that this whole term here needs to be some constant. And the same is going to be true for the other two terms. So in order to add three terms, each with their own variable together that are only dependent on one variable, they all have to equal a constant, or when we added them together, we would still have variables. So what does that mean? It means we have a simpler equation. So again, taking this as an example, it means we have the equation negative h bar squared over 2m times 1 over x of x times two derivatives of x with respect to x is equal to e sub x. And what I can do here is rearrange this to get the following. Two derivatives of our function of x with respect to x is equal to negative 2m over h bar squared e sub x times x of our function of x. Now, hopefully, it hasn't been too long and you can recognize that this is the exact same problem that we had for the one-dimensional particle in a box. And that means it has the exact same solution. So the solution to this problem is, in fact, x of x is equal to some normalization constant times sine nx here, pi x over a. And that means that the same is going to be true for the following. So our y as a function of y is going to be n sine ny pi y over b, and our z function is going to be n sine nz pi z over c. So here we have these three functions that are all the exact same way that we've solved this function last time. What does that mean for the wave function? Well, again, remember that the wave function is just a product of these three functions, and the energy is a sum of the energy values of these three functions. So the solution to these is the exact same solution as before. So the energy value here, Ex, is simply h squared nx squared over 8ma squared. And then Ey is, of course, h squared ny squared over 8mb squared, and Ez is h squared nz squared over 8mc squared, again, because these are just the exact same problems that we had before. So if I wanted to put these back in and figure out what the total Schrodinger equation was, it's simply the product of all of them. I'm not going to have it normalized, so the n here, that is just a constant, so I could put those three together, or I could just leave it out. So I'll just write one n normalization constant there. And then it's sine nx pi x over a, sine ny pi y over b, and sine nz pi z over c. And the energy is simply h squared over 8m, and then we have the product where we have nx squared over a squared plus ny squared over b squared plus nz squared over c squared. And this is the energy of a three-dimensional particle in a box. Now, often what we're going to have is a cube. And if we have a cube, a squared, a equals b equals c, because we have a cube. And then this will simplify into h squared over 8ma squared, and all we have in this brackets are nx squared plus ny squared plus nz squared. If we have a cube. If we have a rectangular prism, of course, that won't work, but often we'll consider a cube. Now, what we can do with this is note the following. So we talked earlier about degeneracy, and here we see our first potential example of degeneracy. And a degenerate state, recall, is that a state with the same energy as another state. because we can't actually identify a quantum state. We can only identify observables, which are things like energy. And so we can say this energy is consistent with, quantum state 1, but if there's multiple quantum states with the same energy, we can't distinguish between the two. So for example, consider a state that's following. Consider nx equals 0, ny equals 3, and nz equals 4. How much energy would this state have? Well, the energy would be 0 squared plus 3 squared plus 4 squared. And that, of course, would be 9 plus 16, which is 25. So our energy would be 25 h squared over 8ma squared. Now consider a different state where nx equals 5, ny equals 0, and nz equals 0. And you'll get, again, 5 squared is now 25. So this state also has an energy of 25. So we have degenerate states. And there are, of course, many other states we could combine that have energies of 25. And that's something to keep in mind here. When we have this three-dimensional box motion, we can have degenerate states. And we'll see more examples of degenerate states as we continue, obviously culminating in things like p and d orbitals. Before we move on to the finite box, I want to stress that what we did here, especially up in this part of the math here, separating out our one function into the product of 3 different functions is something that we will do often in this class. This is a general result. Since our potential energy is independent of the variables that are involved, the solution for that must be a product of 3 independent functions rather than something like sine xy or something like that. That can't be part of the solution. It's just sine x times sine y times sine z. And we'll see that again in various solutions going forward. So now let's consider the next case here, and that is the case of a particle in a finite depth box. So I've drawn the finite depth box here, and we can see a couple of things. So one, instead of having an infinite potential outside of the box, we have some finite potential V naught. And inside the box, we still have 0 potential. So here V equals 0, and outside V equals V naught. Now, you'll notice that we have changed the variables on our box. It's still a box of length a, but now instead of going from 0 to a, we go from minus a over 2 to a over 2. And that, again, that's the reason we set up the boundaries is just to make the math as easy as possible for ourselves. So setting up this problem in this way makes the math easier for ourselves. Now, let's consider how to solve this. And again, we just take the same strategy that we always have. So what we have to do is solve the Schrodinger equation. And just like the particle in the infinitely deep box, we have 2 regions. We have a region where the potential is 0, and now we have a region with the potential of V naught. So we'll take the same approach. We'll start by looking at inside the box. And inside the box, we'll find that our solution is actually the same as it was before. So there's no potential. And that means our Schrodinger equation will simply boil down into the following. It will boil down into 2 derivatives of our wave function with respect to x, and that will equal negative 2me over h bar squared times psi of x. So this is the same. We just saw this for the 3-dimensional box. We saw it for the 1-dimensional box. It's the same. And it has the same solutions. And in this case, the solutions that will make most sense are the trigonometric solutions. So we'll go ahead and we can provide a solution here where psi of x is equal to c sine kx plus d cosine kx. And k is, of course, the square root of 2me over h bar. Now, at this point, you guys might be wondering, why do we have that cosine term? We know the solutions to the particle in the box only have sign dependence. And you'll recall that that cosine term got eliminated because of the boundary conditions. And the boundary conditions for the particle in the box were that it had to equal 0 because there was a 0 probability of finding the particle outside the box. We'll see that complicatedly, maybe unfortunately for you guys doing math here, that is not the case for a particle in a finite depth box. So we cannot eliminate the cosine term. So outside the box, what do? Well, we can solve our Schrodinger equation in the same way. And I would encourage you to go through the math and get to this point where I will just assume that we can all get to. Now our potential, which is multiplied by x in our Schrodinger equation, is non-zero. It's a finite number. And so we can go back and check, and you can, again, look at your notes from last time. You can just follow along with me, or you can pause and actually go through the math yourself. But what we end up with is the following. We end up with two derivatives with respect to x is equal to 2m over h bar squared. And now we have v naught minus e times the wave function. So there was some math manipulating of the Schrodinger equation to get it in this state, and I think that's well within your means to do. Now, what is the solution to this? Well, let's look. So before, we needed to take two derivatives of our function to return our function multiplied by a negative constant. In this case, what are we doing? Well, if our particle is inside of the box here, then V naught is larger than the energy that it has, right? If we're right here, our total energy is less than V naught. And what that means is that 2m times V naught minus e is a positive number. So now I need a function where I take two derivatives of it and return a positive number. So the trigonometric functions are no longer solutions to this Schrodinger equation outside the box. And what is exponentials. So we'll have two exponentials based on whether we are on the left side of the box or the right side of the box. So on the right side of the box, our wave function takes the solution that is the sum of two exponential functions. So it's a e to the minus kappa x plus what we'll call a prime e to the kappa x. And then on the left side, we'll go ahead and write in basically the same solution, but we use a b constant. So we'll say b prime e to the minus kappa x plus b e to the kappa x. Where kappa takes the same form as our k constant, but the potential energy is there as well. So it's 2m, now we have v naught minus e, so it's slightly smaller, and then over h bar. All right, so we can look at these functions and we can note two things. Well, you can say that, well, Dr. Walsh, these can't be good wave functions. We talked about how, according to the first postulate, if the wave function goes on into infinity, if there's an infinite area under the curve, we can't normalize it and it doesn't work. And that's exactly right. So we can use that to eliminate various terms from our wave function. So for example, on the right side, where we're going from a over 2 to infinity, you'll note that this term here, e to the kappa x, would get infinitely large as x gets infinitely big, whereas this term on the left doesn't. So that means that this second term, this a prime term, is not a good wave function, but e to the minus kappa x is a good wave function. It's an exponential decay, which is totally normalizable over an infinite region. And the same will be true for the left side. So on the left side, e to the minus kappa x as we go from negative a over 2 to negative infinity, that will get infinitely large. So we cancel that out as well. And then we have another exponential decay. So our solutions then have trigonometric functions on the inside of the box and exponential decays on the outside of the box. To finish solving the problem, what we have to do is apply the boundary conditions. And the boundary conditions are the same, that our wave function is continuous at the boundaries of the box. Now, this is where it gets a little bit strange, is that in order to make the wave functions continuous at the boundaries of the box, we actually don't set them equal to 0. So instead of being 0, right, what we have is that something like, for example, a e to the minus kappa at position a over 2 needs to equal c sine k a over 2 plus d cosine k a over 2. And this is our boundary condition. And what this will give us is some number, right? They're not necessarily zero, right? If we have an exponential decay, it's starting at some number that's not zero, and it's equaling some other number that's also not zero. And so to actually solve this problem like you'll do on the homework, and if you're listening to this early, I would get a start on the homework. That's pretty complicated. The book will take you through a bunch of steps to actually solve this problem, which is just good practice for you. So what we'll see then is that we get a non-zero probability of the particle existing outside of the box. Now, we can say that, but if we try to think about what it means, it gets a little disturbing. So what that would mean is that our particle is existing, and say, again, it has some potential. So let's put actual numbers on it to compare. So let's pretend it's got a potential of just 20, and it has an energy of 5, and it's existing in this region. But what does that mean? It means that the total energy is 5, 20 plus whatever the kinetic energy is. So in order for this equation to be true, it has to have a kinetic energy of -15. And for that to be true, right, that means we need -15 is equal to 1/2 mv squared. And so our velocity is equal to the square root of -30 over the mass. So we have a non-real velocity with a negative kinetic energy. So for this reason, these areas outside of the box are referred to as the classically forbidden region. And we have particles existing there. So the existence of these particles in the classically forbidden region is one of the strange results of quantum mechanics. It plays an important role in electron tunneling microscopy, as we will see tomorrow. So we'll discuss that technique in detail tomorrow. And what we'll see, we'll actually go back to the slides. So the slides, this is mostly a whiteboard lecture, but the slides will have some figures if you want to check those out as you listen to me talk and write through this math on the board. So we'll go back to the slides and look at it for a brief second here. We can see this leaking has a larger chance of leaking at higher energy levels. So electrons at n equals 1 are mostly confined within the box. And as we go to n equals 5, we see larger leakage from the box. And in this case, what we can see is there's even leakage into an adjacent box. So this explains why core electrons would be less reactive than valence electrons. These core electrons are at lower energy levels. They're held tightly to the nucleus, to not leaking as much. Then when we get to higher energy electrons, they're more leaky, and they're more likely to leak out of the box and maybe spend some time with another atom and then form a bond and react. And so this is just, again, another example that we can see of quantum mechanics helping us to explain some fundamental results that we know from chemistry. I'll leave it off there. Again, the homework will be pretty challenging for today. It involves some careful following through of math, but it's really informative in that we can actually solve for energy levels of particles in a finite box. So I won't make you do that again outside of this homework. I just want you to get some hands-on experience doing this. And again, when we go into class, we spend a lot more time reviewing this. We can go through some of the homework as well in class and actually figuring out what these energy levels come from. And then we will move on next time to looking at electron tunneling.